The industry is shifting toward graph retrieval-augmented generation. Engineering teams are adopting this architecture to solve hallucinations and data blindness in standard systems. The peak performance data justifies this attention. A recent Cedars-Sinai medical trial utilizing GraphRag achieved 94.2. Natural retrieval means knowing the exact difference between a query that requires mathematical rank fusion and a query that requires structural graph traversal. Standard semantic search evaluates meaning. If a user searches for a specific alphanumeric e-commerce SKU, like MBP-M3Max-32-1TB, pure vector search returns irrelevant semantic matches because it is looking for concepts, not rigid keywords. The standard industry fix is to combine dense vector search for meaning with sparse BM25 search for keyword exactness, locked at a hard-coded 50-50 weight split. This split screen shows why these two models are mathematically incompatible. Vector scores cluster tightly on a narrow scale between 0.3 and 0.4. BM25 scores fluctuate on a massive scale from 15 to 50. Adding these raw metrics together causes the massive BM25 scores to completely overpower and nullify the vector scores. The mathematical solution is reciprocal rank fusion, or RRF. By applying the equation 1 over k plus rank, we discard the raw scoring entirely. RRF forces the system to compare the relative rank positions of the documents, merging two incompatible data distributions into a single logical hierarchy. Without normalized rank fusion, any hybrid search pipeline is mathematically compromised. This error leads developers to falsely believe their standard RAG is broken and prompts them to jump to graph solutions prematurely. The next major bottleneck in standard retrieval occurs during compression. Bi-encoders compress entire documents into single vectors upfront. This guarantees high recall, but sacrifices nuanced precision. This upfront compression results in top K retrieval lists cluttered with superficially related documents that all hold nearly identical similarity scores. This is a robust retrieval architecture. The cross-encoder re-ranker acts as the mandatory second stage. A wide net of documents enters the first stage, and a narrow, targeted set drops into the second stage to be precisely reordered. The cross-encoder evaluates the specific document and the specific query together in real time. It utilizes full transformer attention to analyze the exact textual relationship, rather than relying on isolated vector distances. Deploying a cross-encoder solves the vast majority of precision issues that developers mistakenly attribute to a need for GraphRag. A mathematically optimized pipeline, combining BM25, dense vectors, RRF, and a cross-encoder, is the prerequisite baseline any engineering team must build before evaluating graph architectures. Optimized hybrid pipelines retrieve isolated text chunks efficiently, but they cannot synthesize logic that exists in the space between those documents. Tracing the impact of a new global regulation through a specific supplier down to an end consumer product is a query that hits the multi-hop wall. Standard RAG fails this query because it searches for chunks containing those specific keywords. It cannot navigate the sequence of dependencies that exist across multiple separate files. GraphRag addresses this by shifting the computational load away from the moment of the user's query and placing it directly into the initial indexing phase. This is the large language model extraction phase. The system reads the entire corpus specifically to identify entities and relationships. It extracts isolated noun phrases and draws explicit connecting lines between them to form a massive conceptual web. The Lighten algorithm then clusters this massive web into functional groupings. It builds distinct hierarchical communities based on relationship density. This pre-computed structure allows the system to instantly traverse multi-hop logic pathways. When a query is finally asked, the groundwork to generate a summary is already finished. This capability requires 10 to 40 times the indexing cost of standard RAG. It should only be used for problems that strictly demand it. GraphRag is a structural architecture designed specifically to map relational logic that dense vectors simply cannot perceive. If GraphRag maps logic so effectively, we have to look at why the ICLR 2026 data showed it failing on real-world context relevance. We find the answer in the benchmark data for Level 1 questions, simple fact retrieval. For single-hop lookups, the high density of a knowledge graph pulls in logically related but factually redundant data. This messy cluster is structural noise. For Level 3 questions that demand a contextual summarize, the graph succeeds. It navigates multi-step pathways that vector search misses. The empirical findings dictate the rule. Standard RAG achieves 83.2% recall on basic facts, while Graph RAG achieves up to 90.9% recall on complex reasoning. The hidden danger of Graph RAG lies in fragile entity extraction prompts. If the LLM extracts the wrong relationships at index time, the graph will output confidently wrong reasoning at query time. Utilizing GraphRag for basic factual lookups is an architectural error that degrades response relevance by overwhelming the LLM with unnecessary context. The industry debate framing GraphRag versus Standard RAG is a false dichotomy that misunderstands modern system architecture. This is the orchestration router, the modern production standard. A classifier model actively determines the user prompt's complexity. Exact keywords route straight to the optimized hybrid vector pipeline. Multi-document synthesis queries route to the graph framework to retrieve community summaries. Engineering teams must first mathematically correct their baseline hybrid search with rank fusion and re-ranking before spending a single dollar on graph indexing. High-performance AI pipelines function as orchestrated ecosystems where queries are intelligently routed to the mathematics best suited to answer them.